Welcome back to this next video in which we are discussing control of blood pressure and blood volume. Okay, so we're currently in the process of discussing models of the cardiovascular system, and we've started off with this simple model of the cardiovascular system in which we assume that the heart is a single chamber, and we also assume that there is a fixed stroke volume, so the heart is performing according to these specifications here. So there's a fixed stroke volume that is independent, we assumed, of what the pressure in the venous system and the pressure in the arterial system were. Okay, and that had the great benefit that it meant that it was much simpler to understand what was happening. So it was a nice simplification, and it got across this incredibly important concept that you're going to build up this dynamic equilibrium where you have a certain mean arterial pressure and a certain mean venous pressure, and when you have this when you've built up this mean arterial pressure and this mean venous pressure, that will have a pressure gradient across from the arterial to the venous system, which will establish a blood flow through the microvasculature that in the cycle duration of 0.8 seconds is equal to the amount of blood that the heart will move in a stroke volume's worth from the venous side to the arterial side. Hence, we've reached that dynamic equilibrium. So that's the really important concept that this model allows us to understand, and it also allows us to understand how important maintenance of mean arterial pressure actually is. And indeed, when people talk about blood pressure, usually what they mean is mean arterial pressure. This is the most important parameter with regards to pressures and blood, okay? Because as I said at the end of the previous video, this is what determines the flow of blood through a microvasculature network in a certain portion of tissue. So if you've got a certain portion of the brain and it's got a microvasculature network through it, the amount of blood that's flowing through that is determined by the mean arterial pressure. Okay, so the heart's job really is maintaining the same mean arterial pressure within the arterial system, and then if it does that, if it successfully does that, then you're going to have the same amount of blood moving from the arterial system through to the venous system through each of the microvasculature networks all over the body. Okay, so that's this simple model of the cardiovascular system then. What we're now going to do is we're going to upgrade to a more complicated model of the cardiovascular system, but one that we're going to need to understand. And this more complicated one now involves going back on this assumption that we made here, that stroke volume would remain always the same on each beat of the heart, independent of what the pressure in the venous system and the pressure in the arterial system were doing. That is wrong, and we need to remove that now and put in a more complicated model in which the stroke volume does vary with the venous system pressure and the arterial system pressure, because otherwise we're not going to be able to understand the importance of maintaining blood volume for maintaining blood pressure very well. Okay, so I'll go over the page then, and the first thing that I want to do then is just discuss with you stroke volume. Let's discuss stroke volume in more detail than we have previously, and in particular what we're interested in is what actually determines stroke volume, what actually determines how much blood the heart is going to pump from the venous system into the arterial system every single time it beats. Well, firstly, let me just discuss a few concepts with you, and then we'll answer that question. So I'm just going to introduce firstly a bit more terminology. So two pieces of terminology that it's going to be very important for us to understand are the concept of the end diastolic volume. Now remember, we're still modelling the heart as a single chamber, and if you like, you can think of that single chamber as being the left ventricle. Okay, so EDV is the end diastolic volume. That's what it stands for. E is for end, D is for diastolic, and then V is for volume. Now what is meant by end diastolic volume is how much blood is there in that chamber of the heart, which we can imagine as the left ventricle. In reality, when people talk about end diastolic volume, when we're thinking about the heart as having 4 chambers, they mean the volume in the left ventricle at the end of diastole, the left ventricular end diastolic volume. So this means, as the name says, the amount of blood that is in the chamber of the heart, the main chamber of the heart, the left ventricle. In our case, where we're thinking of the heart as just being a single chamber, we can just think of this as the amount of blood in our single chamber at the end of diastole. So remember, every 0.8 seconds the heart is going to undergo systole, and in between the systoles, that period is known as diastole. So end diastolic volume is the volume that's in our one chamber of the heart right at the end of diastole. So the amount of blood that has refilled into the heart from the venous system right at the end of diastole. So going back to our picture, here is the venous system. There is a pressure in that, remember, okay, and that's going to drive blood to fill the heart. Okay, at the end, and by the end of diastole, how much blood have we got in there? That's what's known as the end diastolic volume. Okay, so end diastolic volume means how much blood is there in our chamber of the heart by the end of diastole. Another really important concept with regards to the heart is the ejection fraction, which is written EF for short. So this stands for ejection, that's the E, and then fraction, that's the F. Now this means what percentage or what fraction of the blood that is actually in the chamber of the heart at the end of diastole is actually going to be ejected into the arterial system. Because when the heart contracts, when our single chamber of the heart, which we can think of as the left ventricle if you really want to think of it as one of the chambers of the actual heart, when it contracts, it's not going to push absolutely every drop of blood that's in it into the arterial system. No, instead only a certain fraction of that blood is going to be expelled into the arterial system. So that fraction of blood then of the end diastolic volume that's actually going to be expelled into the arterial system every time our chamber beats is known as the ejection fraction. Therefore, how much blood is actually going to be ejected into the arterial system, the stroke volume, it's just going to equal how much blood is there in our chamber by the end of diastole, i.e. the end diastolic volume, times the ejection fraction. So here we have now a nice equation, a nice equation then for the stroke volume. It's the end diastolic volume times the ejection fraction. And this equation is now going to allow us to understand what is actually going to determine how much blood the heart is going to move from the venous system to the arterial system every time it beats. So, firstly, let's think about the end diastolic volume. What is actually going to determine the end diastolic volume? Well, this is going to be determined by the mean venous pressure, because if the pressure in the venous system is higher, you can imagine that that's going to mean that more force is going to be pushing blood into the cavity of the heart, the chamber of the heart. If mean venous pressure is higher, you're going to have more force driving blood into the chamber of the heart, and therefore you're going to end up with a larger end diastolic volume. So mean venous pressure is actually really important in determining end diastolic volume. So end diastolic volume is going to be determined by mean venous pressure. So this, firstly, we've just seen that this is not independent of what the venous pressure is doing. So the amount of blood in the heart at the end of diastole, ready for the heart to contract down on it, is going to depend on what the mean venous pressure is. And I hope that's fairly common sense. This is refilling this, so of course it will be. Of course, we need to remember that the heart has valves to prevent blood flowing back from the arterial system into the venous system. So the heart is a one-way system. Blood cannot flow from the arterial system to the into the heart. It can only flow from the venous system into the heart. Okay, so how much blood is going to flow into the heart when it relaxes back down? Well, of course, that's going to be determined by what the pressure in the venous system is, i.e. what the mean venous pressure is doing. Right. Okay, now, if you bring in a larger end diastolic volume then, if you fill up the chamber of the heart with more blood, does that mean that the stroke volume is going to go up? Well, logically you'd think no, it can't, because when the heart contracts and pushes blood into the arterial system, it's every drop of blood that it moves into the arterial system requires a lot of energy to move that blood into the arterial system. If the heart is going to move a greater volume of blood into the arterial system, it's going to require a lot more energy to move that in. Now, where is that energy going to come from? Well, it would have to mean that the cardiomyocytes would have to contract harder. They'd have to be generating more force. So increasing end diastolic volume, you wouldn't think that that would actually increase stroke volume. You would imagine that if you increased end diastolic volume, the ejection fraction would have to go down, i.e. the fraction of the blood that you actually successfully ejected would go down, and therefore stroke volume would remain the same. Okay, and I'll remind you the reason for that is because every drop of blood the heart ejects into the arterial system costs it energy. Okay, energy it gets by the cardiomyocytes contracting and using ATP. Unless the cardiomyocytes are contracting harder and using more ATP, you're not going to actually get a larger stroke volume. However, increasing the end diastolic volume does actually increase the stroke volume, okay, because the cardiomyocytes do actually end up contracting harder. So even if the ejection fraction does go down somewhat, it doesn't go down as much as you'd expect it to have to go down. And the reason is that when you increase the end diastolic volume, the cardiomyocytes do actually contract harder. They seem to realize that they've got more blood to expel and that they need to contract harder. And I'll just go into this in a little bit more detail. So this is a very famous law of the heart known as the Frank-Starling law of the heart. Okay, so let me just explain what the Frank-Starling law is. The Frank-Starling law says that if you stretch the wall of the heart more, and of course if you're forcing in more blood into the wall of the heart, what that will be doing is it will be distending the wall of the heart. So if you stretch the wall of the heart more, and there's a fancy name for what is for the stretch on the wall of the heart before it's contracted. It's known as the preload, and this is a concept that people absolutely hate because there's so much misinformation out there about it and so much misunderstanding of this term. Preload, what is meant by preload is at the end of diastole, when the heart's completely relaxed, there's no contraction in the cardiomyocytes, we have forced a certain volume of blood into that chamber, the end diastolic volume here. Now that blood will have a certain pressure and therefore it will be distending the wall of the heart somewhat. It will be stretching it out like the balloon. It will be stretching the wall of the heart out. How much it stretches the wall of the heart, the tension in the wall of the heart, the elastic recoil in the wall of the heart, like any other blood vessel, that is called the preload. So preload means how much you've stretched the wall of the heart by filling it with the end diastolic volume. Now if the mean venous pressure is up, then the end diastolic volume will be increased, therefore the preload will be increased. And the Frank-Starling law says that if you stretch the wall of the heart more before contraction, then the force with which the heart will contract, which is known as the contractility of the heart, will increase. So increasing preload causes the contractility, the force that the contracting myocardium actually generates, to go up. Now, why does that actually occur? Well, let me try and explain simply, and I could make an entire video, and indeed I think I once did, on why the Frank-Starling law actually holds true, but I'll just go over this quickly. So, if we stretch the wall of the heart more, that means that all of the cardiomyocytes are going to be stretched more. So here's a not very stretched cardiomyocyte, and here's a more stretched cardiomyocyte. And the idea is that the reason that the more stretched cardiomyocyte will contract harder and generate more force when it's actually signaled to do so by the electrical activity within the heart is because in the stretched cardiomyocyte, more of the sarcomeres are in a state where they can actually contract. So the idea is in this unstretched cardiomyocyte, a lot of the sarcomeres, which are the contractile units, are already completely overlapping. So if this and that picture's useless, you're not going to be able to see that, so I'm going to draw it bigger here. So if this is a sarcomere here, then these are the Z discs of the sarcomere, like so, and I'll just colour in a few bits. So I'll just do this a bit more properly, so we'll label up the different portions of a sarcomere. So I'm drawing out a sarcomere here. These in green are meant to represent the Z discs of the sarcomere, which of course are the proteinaceous structures that have the actin filaments attached to them. These lines here, horizontally here in blue, these are meant to represent, of course, the actin filaments. So this is the actin filaments. And then, of course, suspended in between the actin filaments, between these two different Z discs, you'll then have the myosin filaments. So here is a myosin filament. And the idea is that in these unstretched cardiomyocytes, a lot of the sarcomeres will already be at a length where they can't really contract that much, even though they're not actually contracting at the moment. This cardiomyocyte is relaxed. The myosin filaments are not interacting with the actin filaments. I'll just label up the myosin filaments here. So this is a myosin filament. Okay, so even though this is a relaxed sarcomere, it's not contracting at the moment. It's already in a state where it can't really contract that much more, because as you can see, the myosin filaments are already very much so overlapping with the actin filaments, and the Z discs are already quite close together. The idea then is that a lot of the sarcomeres in this cardiomyocyte are going to be in this state, and therefore when this cardiomyocyte gets the electrical signal and converts that into a calcium signal, and that calcium commands the sarcomeres to start contracting, this sarcomere isn't actually going to be able to contribute to the force generated. It's not actually going to take part. Whereas if we stretch the cardiomyocyte, lots of these sarcomeres that are already in this state where they're effectively contracted down are now going to be stretched out, and you can imagine pulling these Z discs out, and then they'll be in a state where if the cardiomyocyte does get stimulated to contract, they'll be able to contract. So the idea is that in these stretched cardiomyocytes, these cardiomyocytes in a more stretched myocardium wall, you're going to get greater recruitment of sarcomeres when the electrical signal actually arrives, and that's the reason that the force these cardiomyocytes will generate when they actually contract is going to be increased. So that's believed to be the explanation of the Frank-Starling law, but it's a really important law of the heart that if you fill the heart with more blood, the force with which the myocardium contracts is going to be greater, and therefore the stroke volume will go up. The ejection fraction will not go down as much as you'd thought it would go down. It will still go down somewhat, but overall now when you times these two together, the elevated EDV and the not so much decreased ejection fraction, you will get a larger stroke volume. So contractility will go up, and this causes overall stroke volume to go up. Okay, which of course causes cardiac output to go up, provided heart rate has remained the same. Okay, so increasing mean venous pressure, therefore, does increase the stroke volume. Okay, and contrarily, decreasing the mean venous pressure does decrease the stroke volume. Okay, right, so that's how the mean venous pressure then can change the stroke volume. We also want to talk about how arterial pressure, the pressure in the arterial system, is going to affect stroke volume. So now let me talk about mean arterial pressure. So this is all about how mean venous pressure is going to affect stroke volume. Now I want to talk about how mean arterial pressure is going to affect stroke volume. So if mean arterial pressure is higher, then of course it's going to take the heart more energy to move a drop of blood into the arterial system. A very high arterial pressure, it's going to take more energy to move the blood into the arterial system. Okay, so clearly mean arterial pressure is going to influence stroke volume. Indeed, a higher mean arterial pressure is going to reduce ejection fraction. So mean arterial pressure has an effect on ejection fraction. The higher it is, the lower ejection fraction is. So the higher mean arterial pressure is, the lower the ejection fraction is. Right, so this means that stroke volume is going to be decreased by the mean arterial pressure going up. Now, I want to give another piece of terminology that again has a lot of misunderstanding concerning it, which is the concept of afterload. So preload and afterload. Preload's the slightly easier one. Afterload is the one that people really get confused about. So let me tell you what is meant by afterload, because these are terms that cardiovascular physiologists absolutely love because they know that students won't understand them. So afterload. What is meant by afterload? So both preload and afterload refer to tension in the wall of the heart. Preload, remember, was the tension in the wall of our heart, and we're just modelling our heart as a single chamber. The tension in that single chamber wall due to the stretch on it, because we forced in blood and we distended it out like a balloon. Okay, and that was determined by mean venous pressure, well, by end diastolic volume, which was determined by mean venous pressure, and it determined how hard the myocardium was going to contract. Afterload means, again, the tension in the wall of the myocardium, but it's the tension in the wall of the myocardium right at the end of systole. So the heart contracts, and initially when it contracts, it is building up the pressure in the chamber higher and higher and higher. So the first bit of contraction of the myocardium is actually what's called isovolumetric contraction. And the reason it's called isovolumetric contraction is iso means the same. It means effectively the same as homo. So isovolumetric means the same volume, and contraction means that we are contracting, but the volume is remaining the same. And this is really important to understand. So the myocardium contracts, generates force, generates a tension in the wall of the myocardium. This increases the force inwards on the blood. So if I just draw my picture here, so I'll once again represent my heart as a box here. So if the myocardium is contracting, then we're going to be increasing the tension in the wall of the heart. This is going to be creating an inward force on the blood. Okay, so the pressure of the blood has to go up and up and up and up. But you might be saying, well, why would it not go into the arterial system? Well, until the pressure in the heart chamber gets to the level of the pressure in the arterial system, you're not going to get it moving into the arterial system. You have to get the pressure up to the mean arterial pressure before the blood will actually move from the chamber of the heart into the arterial system. And remember, there's a valve here making sure it doesn't go back into the venous system, so it can't go this way. It's a one-way system. Okay, so the valve preventing it going into the venous system has closed, and it can only now go on into the arterial system. Now, at that phase then, where the heart is contracting but the volume in the chamber of the heart is not getting any smaller, that's known as isovolumetric contraction, and that's the portion where you're just raising the pressure in the heart up to the mean arterial pressure. And at that point, the tension in the wall of the heart is getting higher and higher and higher until eventually you finally do get the pressure in the chamber of the heart up to the arterial pressure, and then the blood will actually be ejected out. Again, that's known as ventricular ejection, because of course it's usually occurring in the ventricles, but we could just call it ejection equally well. So ventricular ejection. So we'll get the blood ejected out into the arterial system. The meaning of afterload is how high did the tension in the wall of the heart have to get in order to create a high enough pressure inside the chamber of the heart to match the arterial pressure to get ejection of the blood into the arterial system. That's what is meant by afterload. So afterload, that sort of tension is created by contraction, whereas preload was created by stretch, not by contraction. That was elastic recoil effectively. This is active contraction that's producing this. So, if the mean arterial pressure is higher, then the afterload that the heart is going to have to get up to is going to be increased. And if the afterload is higher, then that means that the ejection fraction is going to go down, because the amount of, the myocardium has a certain amount of energy that it's going to generate in this contraction. And if the arterial pressure is very, very high, then you're not going to get as much blood moving into the arterial system for that same amount of energy, because we're moving it into that high pressure area. So overall, the lesson from this is that stroke volume does depend on mean venous pressure and also on mean arterial pressure. So both of these influence stroke volume. If mean venous pressure goes down, that's going to reduce stroke volume, and if mean arterial pressure goes up, then that's going to reduce stroke volume. Now let's put that back into our overall model of the cardiovascular system. So now let's have this more grown-up model of the cardiovascular system, where we acknowledge that as mean venous pressure and mean arterial pressure change, then stroke volume is going to change. So here comes the more grown-up model of the cardiovascular system. So same story as before, we've built our tubes, we've put in 5 litres of blood, we've started with this initial situation where the pressure everywhere was equal, and that's the mean systemic pressure around 7 millimeters of mercury. Now what we're going to do is we're going to turn the heart on, and we're going to have the same rate, so the heart rate is going to be again 75 beats per minute, but now we're going to acknowledge that the stroke volume is going to depend on what the venous system pressure and the arterial system pressure are. So initially then, when the heart beats for the first time, you've got a quite high venous system pressure, the highest it's ever going to be from now on. So when we've just started it, it's only going to go lower now than the mean systemic pressure. So the venous system pressure is at its highest, the arterial system pressure is at its lowest, therefore the stroke volume is going to be at its highest. So the first beat is going to have the highest stroke volume. And again, what will happen is that will create a pressure differential between these two, and then you'll get blood moving from the arterial system back to the venous system through the microvasculature. Now, of course, from the first beat, you won't get all of the blood that was moved into the arterial system from the venous system by the heart returning, so you'll get the gradual build-up of arterial pressure and the falling down of venous pressure, and this will continue on. So you'll continue on in this way, building up arterial system pressure and falling down venous system pressure. Now, in the first model, we just said that we were waiting to create a pressure difference between the arterial and venous systems that will create a flow through the microvasculature that equaled the stroke volume. So this was the thing that was varying as we were building up the pressure difference. But now we have to acknowledge in our more grown-up model that as we build up this pressure difference, and as venous system pressure falls down and arterial system pressure goes up, that's going to be reducing stroke volume. So actually the two things are moving to meet each other. Stroke volume is gradually going down. The amount of blood returning from the arterial system to the venous system in a cycle duration of 0.8 seconds is increasing. So they're just, one's falling down, this one's rising up to meet this one, and then the dynamic equilibrium will arise when the two are equal to each other, when the stroke volume has fallen down to now a level that the amount of blood moving from the arterial system to the venous system in that cycle duration is equal to. And by the way, there's a term that I'd like to introduce, which is a term meaning the amount of blood to move from the arterial system to the venous system, okay? And this is known as the venous return. So venous return means how much blood moves from the arterial system to the venous system through the microvasculature. And if I say the venous return in 0.8 seconds, i.e. in one cycle, then I will mean the amount of blood moving from the arterial system to the venous system in that amount of time. Usually if someone just says the venous return, they'll mean in a minute, like cardiac output is the amount of blood the heart moves from the venous side to the arterial side in a minute. Okay, but if I say venous return in 0.8 seconds, I hope it will be apparent what that means. Okay, so that's the more grown-up model, that the stroke volume is going to gradually fall down and the venous return in one cycle is going to rise up, and when they are equal to one another, that's when you will have reached the dynamic equilibrium. And all of the all of these numbers that I've given you concerning what systolic pressure, diastolic pressure, pulse pressure, mean arterial pressure, and mean venous pressure are at that dynamic equilibrium are the correct values. Okay, that's just the more grown-up, complicated model for how it's actually produced. Okay, so we'll have a break there, and in the next video what we'll begin to talk about is the sort of things that could actually result in a change in blood pressure, change in mean arterial pressure. And remember, from now on when I say blood pressure, fill it in with mean arterial pressure, that's what I mean by it. And we will see how blood volume, a change in blood volume, could impact blood pressure. And then we'll begin to talk about the homeostatic mechanisms that exist in order to try and maintain blood pressure and also blood volume.